אוקיי. יש טעם לחכות עוד, את חושבת, או ש...
כן, רק 11 עכשיו. אני בדרך כלל מחכה 5 דקות.
אוקיי.
כן, אני אסגור את הרעשים שלי.
אני סגרתי את הרעשים.
כן.
אני רוצה שיש סיכוי שיותר טוב לראות אותה מוקלטת מאשר בזמן חי.
למה?
כי אתה יכול לעצור את הוידאו ולחשוב על התשובה של השאלה.
לא חשבתי על זה.
אבל בסדר, עכשיו פה אני מסביר איך להסביר את התשובות. ומה לומדים מהם.
טוב, יופי. האמת שההרצאה הקודמת שהעליתי, אנשים כן ראו והגיבו, אז
כן.
אני חושב שזה גם דרך טובה.
איך באופן כללי עם הקומיוניטי, הכל בסדר?
כן, כן, כן. היום יצאנו לרוץ בבוקר. מרגש ונחמד מאוד.
הבנתי שזה משהו שבישראל אי אפשר ממש לעשות.
אפשר, אבל אסור. אנשים עושים אותו.
כן. והתחלנו פאזל של 1,000 חתיכות אתמול.
גמרתם כבר?
לא, עבדנו עליו, אבל יותר מ10 שעות. כן. היי, אמא! כן, זה פאזל קשוח. אבל בסדר.
זו תמונה של המון מקרונים בצבעים שונים. עכשיו, הצבעים הם שונים, אבל יש 5 צהובים, 7 כתומים, 7 ורודים, אז הכל נראה מאוד דומה.
יש לחבר שלי, אורן, אמא שלו אוהבת פאזלים מאוד מאוד קשים. אז ליום הולדת הוא קונה לה תמיד פאזלים מסדרה שנקראת ה-Impossible. אז אחד מהטריקים המקובלים זה שהתמונה נמצאת בשני הצדדים.
וואו.
וגם זה כאלה כמו ה-101 Dalmatians, בשחור לבן.
וואו. שני צדדים.
וכדי שזה לא יהיה קל מדי, אז כשחותכים את זה, הם כל הזמן מסובבים, שלא תוכל להסתכל על החתיכה ולראות איפה הלמעלה שלה.
מה? מה זאת אומרת?
אם אתה מסתכל על החתיכה, אתה יכול לראות לפי החיתוך איפה הצד שלה למעלה, אם אתה מיואש.
אוקיי.
לא חשבתי את זה.
דואגים שלא תוכל לעשות את זה. וכיוון שזה עדיין ממש קל, אז אין לזה בורדר. זה לא בתוך צורה, אלא בורדר כללי סתם אקראי.
Close the door, please. סליחה.
וואו.
והדבר האחרון זה שחסרות 2 חתיכות ויש 3 חתיכות ספייר.
אוי, זה נשמע סיוט.
אבל זה רק 600 חתיכות, אבל הוא אומר שאמא שלו אחרי כל דבר כזה, איזה יומיים היא לא ישנה עד שהיא גומרת את זה.
וואו. זה נשמע ממש לא כיף.
טוב.
אוקיי.
בוא נתחיל.
אז אני אתחיל?
כן.
תודה.
עם בדמה? אז אני הולך לספר היום... I'll switch to English. Okay, so I'm going to talk about riddles and how you can learn from riddles. And you can learn from riddles all sorts of interesting concepts. So I will start with mass and weight. And basically the way I will do it is I'll explain the riddle. And then I'll ask you if you have any questions to understand the riddle. And then I will say, okay, for those on the videos that are watching it offline, they can stop and try to figure it out, and then I'll explain the result. So the first riddle is the following. Assume that you are on a pool. You have a pool at your house, and you are on the pool with a little boat, and you take something heavy like a stone or something, and it was in the pool. It was in the boat, and you put it on the side, and it goes into the water, and you go blub, blub, it goes to the bottom of the pool. And the question is,
Wait a minute. I didn't understand. The stone is in the boat? Is that what you
Yes.
said? Okay.
It's in the boat in the beginning, and you take it on the side and you drop it, and it drops into the water and to the bottom of the pool.
Okay.
And the question is, does the level of the water in the pool goes up or down or stays the same? So is the question itself clear?
Yes. Mhm.
Okay. So those are hard questions. So now I'm going to explain the reply. And the reply is that when the stone is in the pool, the amount of water that it displaces depends on the volume of the stone. So if it's a small stone, it displaces a small amount of water. And if it's a big stone, a lot of water, depending on how big it is. When it's in the boat, the amount that it displaces depends not on its size or volume, but on its weight. So if it's very heavy, it drops the boat down a lot. And if it's very light, it doesn't drop the boat down a lot.
Okay.
So if we had a very small stone which was very heavy, like say made out of gold, then in the boat, it would drop the boat a lot, but outside the boat, it would displace a little amount of water. And therefore, the water would go down. And this is actually true for any stone, because if it is going down in the water, and we said that it goes down to the bottom, it means that it weighs more than its volume. It weighs more than in volume in water, and therefore in the boat, it dropped the boat, it was heavier, it pushed the boat down more than it would do in the water. So basically, a thing will go into the water and go to the bottom only if its weight in water is bigger. I mean, the volumes of the water that weighs the same as it is bigger than the stone itself. Joyce, is this clear, the explanation?
Yes, I understood that. Okay.
Okay, so we started with that, and we said that if we had a stone in the boat and we dropped it into the water level would go down, because in the water it will display a little bit, and in the boat it displays a lot, so to its weight. So now let's go to the second
Well, wait a
question, and
minute.
let's assume.
No, wait, excuse me. But
Yes.
that would make the water level go up a little
The
bit.
stone makes the stone in the water makes the water level goes up. So if I just throw the stone from outside the pool into the water,
Right.
then the water level would go up.
Yes.
And it would depend on the volume of the stone. It doesn't matter how much the stone weighs, right?
Right. Okay.
Right. But I'm actually doing it not from the outside the pool, but from the boat itself.
Uh-huh.
And in the boat, it displays a lot more water because it's heavy. So think about a little boat and you push it, and then it goes a lot more into the water and it displays a lot of more water.
Right. Okay. Right.
Okay. So let's assume that you were in the boat, and what you throw outside was not the stone, but wood. And the wood floated on the water. So you were in the boat, and instead of throwing stone into the water, you threw wood into the water. And again, we have the same question. Will the level of the water in the pool go up, down, or stay the same?
But wood floats, right?
Wood
Usually.
floats, yes.
Right.
So
But some of it is in the water anyway, right? A little.
Right, some of it is in the water.
And some of it is out of the water, right?
Right.
So it would go up.
Actually, it would stay the same. And the reason it would stay the same is that when it's in the water, the amount of wood that goes into the water is exactly equal to its weight in water, to the weight of the entire wood. So if we have 1 kilogram of wood, its volume is, say, 2 liters. The weight of water of 1 kilogram in water is exactly 1 liter. So half of it is in the water and half of it is outside. So the amount of wood that is in the water is exactly is exactly the volume of the waters that is equal to the weight of the wood.
Mm-hmm.
And when it's in the boat, it displaces the same. It pushes its own weight. So when it's in the boat, it pushes its weight, and when it's in the water, its weight is in the water, the rest is outside.
Right.
And therefore, the level of the water will stay the same.
Huh. Okay.
So now the third question of the same type. So we have an ice cube, which is in a glass.
In a bus?
In a glass.
Glass. Okay. Yeah.
You have a glass, and in the glass you have water, and in the water there is an ice cube.
Right.
And the ice cube melts.
Right.
Will the level of the water in the glass go up or down?
Well, when it's an ice cube and it's solid, there's no level of water. As it melts,
No,
the
no,
level of water goes
it's
up.
floating in the water.
Oh, okay. Yeah.
So you have water, and in it you float an ice cube to make the water colder.
Right.
And eventually the ice cube melts. And the question is, will the level of the water go up or down?
Up, I think.
It would stay the
Okay.
same?
It stays the same.
Oh.
For the same reason, because the amount of ice that is in the water, the amount of ice that is, yes, the amount of ice that is in the water depends on the weight of the, on the weight of the ice, right? So it usually, ice is a little bit lighter than water.
Mm-hmm.
So 9/10 of it is in the water and 1/10 of it is outside because it's a bit lighter than water. And once it melts, basically it fills the same space again because water is heavier than ice, and the level of water will stay the same. So those questions are actually kind of confusing. And now let's see how they implicate something else. So if you have an iceberg in the sea, and the iceberg melts, what happens to the level of the sea? It goes up, down, or stay the same?
Well, I mean, without even anything that we've been discussing now, everybody talks about the icebergs melting and that is raising the sea level, and there are going to be floods. But that's not answering the logic of anything you just talked about. I mean, I think that's right. That's what I've heard. No, but,
Right.
Right.
But by the logic of what we talked about, when an iceberg melts, the sea doesn't go up, it stays the same. So the questions that I have is, why does everybody talk about ice melting and the sea going up? If when an iceberg melts, the sea doesn't go up, and you can either trust me or figure it out for yourself, but that's the way it is.
So why does everybody talk about it?
That's a good question. Well, the reason is that most of the ice that we have is actually on land.
Ah.
And if it melts, then it goes into the sea, and then and then the sea goes up. Okay?
Okay. Got it.
So later you can figure out those questions. They're not so easy to do in real time. I mean, when I don't give you time to think about it. So now I'll give you one more question which doesn't make any sense whatsoever. But it's a question. And my daughters know that if I ask a question, the first answer is probably wrong. So the question is, what does weigh more? A kilogram of, say, iron, or a kilograms of feathers? So basically, the question is the following. You take a weigh on which you put something, like if you put myself on it, it will say 100 kilograms, okay? So you put something on it, say a kilogram of iron, and then it says something. And then you put a kilogram of feathers, and it says something else. Is it the same thing or not?
Isn't a kilogram a kilogram? I mean,
it is.
So there'd be much more volume of feathers to get to a kilogram than whatever the second thing was, I forgot. But I think a kilogram's a kilogram.
Iron. The second thing is iron.
Iron.
Right. So so obviously a kilogram is a kilogram, but the weight doesn't measure kilograms, it measures weights. Kilogram is a measure of how much matter you have in you. So for example, if I will go to the moon and I will stay on the weight, I still 100 kilograms, but the pressures that I will put on it will be more like 17. And that doesn't have anything to do with a diet.
Right.
So we're trying to figure out the difference between weight and in this case, and mass. And kilogram is a unit of mass, not of weight. So to give you a clue, let's assume that instead of putting the weight inside in the air, I would put it inside the water. Okay?
Yeah.
And then I will put the iron on it, and it would weigh something. But if I would put the feathers on it, they would weigh nothing because they float in the water. Right?
Okay. Yeah.
We have negative.
Yeah. So when we put the weight, normally the feathers, although we don't think about it, they actually float a little bit in the air.
Right. That's true.
So if we put air, a kilogram of air, which is a lot of air, but still a kilogram, it's a mass, then it weighs nothing, even though it's a kilogram, right? I'll take a kilogram of air and put it on the weight. It doesn't weigh anything because it floats in the air.
Can you have a kilogram of weight of air?
Yeah, for sure. Why not? It's quite a lot of air. It's when you take a hot air balloon, there is lots of kilograms of air inside.
Okay.
So the answer is that a kilogram of feathers will weigh will weigh a bit less than a kilogram of iron because the feathers float in the air. And since you have more volume of them, they will float more, and therefore it will weigh less. And one of the things you can realize about it is you start with something sort of in the middle. You start with something really heavy, and you start with something really light. And if it's really light, like air, then it weighs nothing, right? You take a kilogram of air, and it floats in the air, and it weighs nothing. So you say, well, let's take something a bit more heavy than air. Then it weighs something, but something is less than a full kilogram. So you go all the way from 0 to something, and feathers is someplace in the middle. Okay. So we talked about those, and now we'll talk about some other things which are sort of basics in physics, but I think interesting in the sense that most people actually don't understand why they happen. So when you have a window, and you look through the window, it's clear, and you can look outside through the window. But if it's dark outside and it's brightly light inside, the window suddenly turns into a mirror. Right?
Mm-hmm.
Yeah.
So why does that happen? Why does the window turn into a mirror at night?
He's the physics student.
Yeah, well, I know he knows, but not everybody knows.
I don't necessarily know. I don't necessarily know. It's not the things we used to learn in our physics classes. I don't have any physical explanation. Maybe just it's a matter of which is more yeah, not for the recording. Who's more dominant? Which light is more dominant? So yes. If in daylight the window also serves as a mirror, but the light from outside is much stronger. So.
Excellent. So basically the mirror, the window reflects some percentage of the light, let's say 5%. Mm-hmm. And during the daytime, when you have 5% coming you from the inside, which is reflected, and maybe 50 times more from the outside, then you don't see the 5%. You don't see it as a mirror because you see just the outside, because you have the strong outside versus the very weak inside. But at night, the 5% from the inside is a lot more than the outside, if the outside is dark. So you don't see the outside because the 5% basically goes over the inside. So nothing changes about the window, but what happens is that if you compare what is reflected to what's coming from the outside, at daytime, what comes from the outside is a lot more, and at night it's a lot less, and therefore it would serve as a mirror. So when you're talking about a one-way mirror, it's enough to be in a dark place looking outside. The people from outside will see it as a mirror, you will see it as a window. Okay?
Okay.
So now I'm going to go into a different question, which is well known, but the well-known solution is wrong. So the question is the following. We have an infinite, this is ideal thing, so don't think about coefficients of whatever. So we have we have an infinite rail tracks, and every meter between them there is, pardon?
Rail tracks, R-A-I-L, is that what you're saying?
Yeah, like for the same as you have for trains.
Yes, okay, I just didn't understand, yeah.
Yes, and every, my English is sort of interesting in that way.
Yeah.
You know the story about this Polish guy who came to England?
And?
And they asked him, why did you come to England? And he said, well, I want to polish up my English. So they told him that his English is Polish enough.
Yeah, right.
So anyway, so we have this infinite rail, and between, there is every 1 meter there is a rail. And there is this mouse, that's going to run around, and he's running in one direction, and there is a bell that is tied to his tail with a short rope. And whenever the tail hits a rail, it goes ding, and when the mouse hits the ding, hears the ding, he multiplies his speed. So he starts going at 1 meter a second, and it goes ding, and it goes 2 meters a second, it goes ding, and it goes 4 meters a second, it goes ding, and it goes 8 meters a second, and so forth and so on. And the question is, what speed will eventually the mouse finish at? Is the question clear?
Yes, but I just want to make sure you said that there's an infinite number of rail tracks, right? Is that what you said?
Yes. Yeah.
Okay. Wow.
So in theory, in physics, you cannot pass the speed of light.
I remember the answer.
But that's not the answer. So anybody can figure out a solution?
I also heard it once, so it's all up to you, Joyce.
Oh, yeah.
No pressure, though.
Yeah, not right. I can't figure it out because.
Okay, Joyce, I'll just say that I'll just make the reply. It's actually not that easy.
Okay.
So the first thing to observe is that the mouse cannot. The air travels. The sound travels at some speed, which is called the speed of sound. Okay.
Mm-hmm.
So if it makes a ding, so once it passes the speed of sounds, and if you start 1, 2, and eventually it gets to 512 meters per second, you will be faster than the speed of sound, and then you will not hear the dings that you make. Okay?
Okay.
So the common solution that people think about is that they will get to something above the speed of sound, and then the mouse will stop going faster because he will not hear the dings that he makes. Okay?
Yeah.
But the trick is that the sound is moving like basically like a ball that is getting bigger and bigger, like a wavefront. And if you move faster than the speed of sound, you're going to catch the sounds that you made yourself because now you're running and catching it the second time.
Mm-hmm.
So for example, if a sound passes me and I hear it and then I start running very fast, I can catch it again. And then I will hear it a second time. So every time you multiply 2 to the 9 times to get to 512 just because you hear it, and then you do it again when you pass them again. So it's 2 to the 18, which is kind of fast, but not quite the speed of sound.
But then wouldn't it just continue because you can catch the waves even further?
Yes, but after you catch them, you're after them and you're faster than them, so they'll never catch you.
Yeah.
Okay.
Okay, so now I'm going to ask a riddle that is related to Corona.
Oh.
And this riddle gets people very, very confused. The worrying thing is that it gets doctors also very confused. And that's not good.
No.
It happens every time, and people actually have to understand it. So the riddle is the following. Let's assume that something is rare in the population. Usually we talk about cancer, but let's say Corona. And let's say that 1 in 10,000 people on average have it. Okay, it's a rare condition. And you were sent to a test for that, but you were just sent for a test, not because somebody suspected that you have it. It's a random test. You're a random person sent for a test. It happens with doctors. The situation which I'm talking about is when they know that something is wrong with you, but they have no clue, so they test everything. So it's not that they suspect you of having it, but
they test everything or they test everyone?
No, I'm saying you come to the doctor, he doesn't know what's wrong, so he starts doing random tests. He doesn't know why you have it.
Like
So
in regular life, not related to the question right now.
Yeah.
Okay.
So let's assume that the test is a good test in the sense that 99% of the time it's accurate. So if you have Corona, 99% of the time it will say you have Corona. And if you don't have Corona, 99% of the time it will say you don't have Corona. So the question is, given that you passed the test and the test said that you have Corona, what's the probability that you actually have Corona?
99%.
So this answer is good in the sense that more than 50% of the Harvard medical students thought so.
That's wrong. I got it.
But it's wrong.
It's the 99%, but times the chance that you have it, which is one in 1,000. Wait, 1 in, I don't know how many you said, 10,000.
Yeah, 99% times that, what does that mean? You don't multiply percent by numbers.
What times 1/10? No, I mean 10%.
Okay, so I'll explain the solution.
Okay.
So if you test 10,000 people with a test like that, 100 of them will show to have Corona even if they don't, just because 1 in 100 it makes a mistake. So 1/100 of 10,000 is 100. So 100 people that are healthy will be shown by the test to be sick. Okay?
Mm-hmm.
And the sick person will also probably shown by the test to be sick. So let's say about 100 people are shown to be sick, of which only 1 of them is really sick.
Mm-hmm.
So the probability that you are sick, if the test said that you are sick, is 1 in 100. Now, why is this important? Because often they give you tests and they don't know, and then they said, well, the test is very good, it's 99%. So now you are sick, and therefore we have to treat you as if you are sick, and some of those treatments are really bad. So you have to actually understand the probabilities, and unfortunately, most doctors don't understand the probabilities. Did you understand the solution that I just gave?
Okay, but what should a doctor do then? Let's say they do understand what your solution was. Then what do you do?
There are a number of options. The best one is to do another test on you and check again if those tests are independent. So if they do another test on you and they check again, then you're likely sick if it shows that you're sick. Why is that? because it was done on 100 people, of which one is sick. So now when you do the test, only one of them will show sick, or actually two. One of the healthy one and one of the sick one. So now it will be 1 in 2 probabilities that you are sick after they do it a second time. But this is only if those tests are independent. I'll explain what independent means. Let's assume that what the tests check your blood pressure. And a certain blood pressure is a good indication that you are sick. If you do it again, it will show you the same thing again because you have the same blood pressure. So you need tests that the two tests should not have the same result. They should be not related to each other. Okay.
Okay. Well, Shmuel, did you tell this to anybody? I mean, it's very important. I'm serious.
Yeah. It's not an invention of mine. People know about that.
Oh, okay.
Unfortunately, most doctors don't. But there are all sorts of things that you need to know to supervise doctors when they do things. The next question. I'm going to give you the example, the original one, but then I'll show you how it's actually relevant to Corona. So, so the question originally was the following question. You are going to have a party tomorrow. And you have lots of barrels of wine. And somebody put really potent poison, you were told, in one of those barrels of wine. And any amount of this poison would kill a person, any amount. But it's a slow-acting poison, so it takes about a day. So you can do only one test, or you can do many tests, but they have to be done at the same time. And the question is, how do you figure out which barrel has the poison in it? So fortunately, you have slaves, and you can give them wine. But it will be desirable not to use 1,000 slaves. So one solution is to give each slave a little bit of wine from each barrel, for each slave from one slave from barrel number 1, another slave from barrel number 2, and so forth. And then within one day, this would work if you had 1,000 slaves. But what could you do if you had few slaves? What's the smallest amount of slaves you could use? The question is not how to waste the least amount of slaves, but how to have what can be done if you don't have many slaves. How can you test all the wine?
How many bottles of wine are there?
1,000.
1,000. Okay.
So for example, what you could do is you can give the first slave wines that you mix from 100 of them.
Right. I was just going to say, can you give a slave, let them taste from more than one bottle, one particular slave? Yeah.
Yes, you could. But the issue is the following. Let's assume that that you gave 10 slaves and each of them got a mix from 100 bottles.
Right.
Then the day passed, and because it's a slow-acting poison, by the end of the day, you'd say, okay, slave number 9 died. So the bottles from 800 to 900 I can't use. That's not good. I want to use all my bottles except one. I want to know which, or cask. I want to know which cask is the one with the.
How about having each slave drink from 111?
Yes.
Different barrels, and then you have so let's say you have 10 slaves. One drinks from the ones that are 100 to 110, and then 211.
Yes.
And then so on, and then you can sort of correlate.
How?
maybe I don't have it. I don't know.
Okay, so I'll explain the solution. So the solution, you wanted to say, Tomer?
I thought maybe apply a binary search, split it into 500, 500. I don't know if you're time limited, but
yeah, you're time limited. You have to do it all at the same time.
all at, at one day.
Yeah.
Yes.
In one day.
Okay, so binary search isn't relevant.
Right. So actually it uses a thing which is sort of similar to binary search, but it's not binary search.
Yeah.
So what you do is you look at it. You look at each slave, and you prepare 10 barrels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just 10. And each slave, his number, each of those, and what do we put in each barrel? In the first barrel, we look at, this is the 0 place in binary. We put all the all the battles that has 1 in the 0 place. This is all the odd numbers. So 1 and 3 and 5 and so forth. And then in the second place, we put all those that have 1 in the 4th place. And in the next one, we put all those ones that have 1 in the 8th place, and so forth. So now, when people drink the wine, and some of them died, so let's assume that people that died were number 1, 3, and 4. Then the slave is equal to 16 plus 8 plus 1, the barrel that is actually poisonous, which is 25. This is the barrels that have, the only barrels that poisoned exactly those combinations. I'm actually going to explain it a bit later and outside, but this is the idea. And the reason I'm going to do it outside is because people look at me as if they sort of forgot their binary. But the idea is basically that you write it in binary, and then you see who died, and you can figure out the binary number. But I think this will be a bit too long to explain, so maybe it was not a very good one for this one.
Oh, it's interesting though, and I'm going to think about it.
Okay, so let's go now into a simpler one. So you have 100 switches, and all the switches are off. Each is connected to a light. And then a frog jumps on them. And he jumps on them, 1, 1, 1, 1, 1, 1, 1, 1, jumps on all of them, and all of them are on. And then he jumps on all the 2s, 2, 4, 6, 8, so forth. And all the even ones are on, and all the odd ones are off. And then he jumps on all the 3s. And then he jumps on all the 4s, and so forth. So after a while, he jumps on 10, 20, 30, 40, and then he jumps on 21, 42, 63, until he jumps on 99, and then it finishes. And by the end of that process, some of the lights are on and some of the lights are off. So for example, 1 is jumped on only once, right? The first time he jumps on 1, and it will never jump on 1 again, so 1 is on. And 2, he jumps on it when he jumps on 1, and also jumps on it when he jumps on 2, so it will be off. And 3, he jumps on it when he jumps on 1, and he jumps on it when he jumps on 3, because he doesn't jump on 2, so 3 is also off.
Right.
So the question is, what do all those that stay on have in common? Is the question clear?
Yeah. They've either been jumped on just once or an odd number of times, I think.
Right, so the question is if it jumps on it an even number of times or an odd number of times. You are correct.
Right.
Lee, can you hear us? Okay. Sorry.
Even number.
Sri, we can't hear you.
I'm not sure if he's
Yeah.
here on purpose.
Okay, so any thoughts on which are the ones that are?
You want to speak?
Zvi, are you talking to us? Okay.
Maybe he's having a problem with his microphone.
Okay. Any of you have an idea of what is which will be on
No.
and which will be?
Oh, Marilyn, hi. Oh, okay. Marilyn, okay. She's muted herself. It was Marilyn.
So Rotem, do you have a clue or Tomer?
I think it's the ones that are that have a quadratic root.
Quadratic. Why quadratic?
You know, the one that are that like you know, 4, 9,
Square
1.
root.
What?
Yeah. It's a square root. It's not
Squared.
quadratic root.
Ah,
Yes.
yes, squared. The ones that are squared. 1, 4, 9.
Exactly. Can you explain why?
Because they let's see. I thought about 4 as an example.
Yes.
So it's divided. Oh, wait, maybe I think I know. For a switch to stay on, it means it has to be switched an odd number of times.
Right.
Right.
So if you take a number which is it has a square root,
Yes.
it means that the numbers it is divided by, the number itself is, or the number which is the square root is counted twice.
Right.
Which makes it the same number. So instead of having an even number of numbers which is it is divided by, it only one of them is counted twice. So it's actually the same one, and that makes it an odd number.
Exactly. So I'll explain it again. So let's assume that you have a number like, say, 62, whatever, a number. And it has things that is divided by. If one of them is smaller than the square root, let's say 2 is smaller than the square root, then there is another number which is bigger than the square root, which is divided by. So 2 times 31 is equal to 62. So this is even. And 1 times 62 is also equal to 62. So everything that is smaller than the square root and everything that is equal, you'll get pairs, and the pairs cancel each other because you press twice. But the square root itself is pressed only once if there is a square root. Because if you have like 64, then it's 8 times 8. So you don't press 8 twice, you press it only once. So then you get an odd number, and that's makes those numbers special in this case, and those are the ones that will remain lighted.
Well, I have to review my math from high school and college about 50 years ago. I'm sorry. I mean, it's all familiar, but boy, I haven't thought about these things for so many years. But okay, I'll keep going. I enjoy it.
So now we have 2 more questions.
Yeah.
And they're actually, we'll start with the one which does not require mathematics, but it's actually really, really difficult, although it sounds simple.
Okay.
So what's difficult about it is that only 40 years ago, somebody realized that this question could have an answer.
Oh.
And then they solved it. It's actually not that hard to solve once you realize that you can solve it. It looks impossible. But once you solve it, it actually opened an entire new field in computer science. So now I'll explain the question. So there is this world, and in this world there is homeowners, and there are people that don't have a home, and they just are servants, and they are outside.
They just what?
Servants, they are outside, they are messengers.
Oh, servants. Okay, yeah.
And the homeowners have something very special, which is a suitcase, and they also have a lock with a key for the suitcase. And if you lock something in a suitcase, let's say I want to give a book to Rotem, what I do is I lock it in the suitcase, and then I can send it to Rotem, knowing that nobody will steal my book. The suitcase will arrive and nobody will take the book. There is only one slight problem, And the slight problem is that Rotem can't take my book either because she doesn't have the key. Right?
Right.
So the problem is I want to send a book to Rotem, and those sneaky devils that I'm going to send it with steal everything, I mean anything which is not inside a locked suitcase. Okay?
Mm-hmm.
So the question is, how can I send something to Rotem? And what happened is that if I will want to send my lock to Rotem, because I have 2 keys, if the lock is not tied to the suitcase, the people will steal my lock. And if it's tied to the suitcase, Rotem can't take it. Okay? So the question is, how do I send something to Rotem? And it's actually, the question itself is not so difficult as such. It's difficult, but it's not amazingly difficult. It's just very difficult.
Mm-hmm.
Realizing that it has a solution was what set it apart. And the solution is actually pretty simple. The solution is the following. I will put the book in my suitcase and I will lock it. And then I will send it to Rotem. And Rotem, she can't open the suitcase, but she can lock it. So she locks it with another lock, which is put right next to mine. And she sends it back to me. And I take my lock off and send it to Rotem. And she takes her lock off and opens the suitcase and takes the book out. So it's a hard solution, but not amazingly so.
Okay.
But what it enabled to do in computer science is that it's enabled us to, I want to talk to Rotem, and somebody really powerful like the United States is listening. And we have never talked before. So to talk, we have to agree on a secret. And how can we agree on a secret between us if we have never talked before and the United States is listening? And this is exactly the way to do it. So I lock the secret, and she locks the secret again, and then she sends it to me, and I remove my lock and send it to her, and she removes her lock. And even though we never talked before, and somebody listened to everything we say to each other, we can actually agree on a secret, which is an amazingly powerful thing in computer science.
Mm-hmm.
But the really interesting thing about this question is not that it's so hard, but it took a long time to figure out that it's actually possible. And it's a nice solution.
Yeah, yeah.
Is the solution clear?
Yeah. I have to keep thinking about it, but yes, I think so.
Oh, I think my dad froze.
Yeah.
I frozen? Am I fine now?
Oh, now
Yeah,
you're good.
now you're okay. Yeah.
Okay. So now for the last question. And it's another famous one, and it has another twist.
Hey, let's hear.
And it's about induction. So it does require mathematics of 11th grade, unfortunately. Actually, it doesn't. Well, it is actually one of the ways used to teach it.
Well,
So the question is the following.
Go ahead.
In Baghdad, it turns out that some of the women cheat on their husbands. And every man in Baghdad, there are all mathematicians there, he knows about all the women if they cheat, except his own woman, on which he doesn't know if she cheats. Now, if a man finds out somehow that his wife cheats, what he does is in the evening of that day, at midnight, he takes a gun and he shoots her. And everybody hears the sound and knows that he shot his wife. And this has been going on for a while. And one day, the Caliph of Baghdad, who is both all-knowing and truthful, said, there are cheating women in Baghdad. Now, everybody knew that there were cheating women, but now he said that. And the question is, let's assume that there are 14 cheating women in Baghdad.
How many?
14.
14.
How long will it take until there are no longer any cheating women in Baghdad? And I think this will be a bit too hard to solve now, so I'll explain the solution. And the solution is called by something called induction. So let's assume that there was one cheating woman in Baghdad, okay? Just one. So everybody knows about one except her husband, who knows about how many?
0.
0. But the caliph, and the caliph knows everything, said that there are women. So on that day, because her husband knows of none and he knows of everybody except his wife, he knows that his wife is cheating on him, so he shoots her. Okay? So if there was one, it's clear that on the first day he would shoot her because he doesn't know of anyone. Okay?
Okay.
Bottom? Let's assume that there were 2, not 1, but 2. So everybody knows about 2 except 2 people that know about 1, right? So what those 2 people that know about 1 except 2 happens that after the first day, the husband is going to shoot his wife because he doesn't know about that 1, right? We solved it for 1 before. So if I know about 1, what I expect is that the husband will shoot her on the first day. What happened when he doesn't shoot her? I know that she's not the only one. So if there are 2, on the second day, the 2 will be shot. But what happened if there are 3? If there are 3, everybody knows about 3 except those people that know about 2. And those people that know about 2 expect that that they will hear the shot on the second day. When they don't hear a shot on the second day, on the third day, they shoot the wife. So if we continue this way, you'll find out that on the 14th unfortunate day, the 14 people will shoot their wife, and this will be the end of the cheating women in Baghdad. So later you can think about it, but now we'll come to the twist, which is the end of this talk. So let's assume that those cheating women are also mathematicians. And they figure out that something really bad is going to happen on the 14th day, right? That's not going on to end well. So what they do is each one of them takes the rifle and takes the pin out of the rifle because she doesn't want to be shot. And on the 14th night, all those men come to shoot their wife, but the rifle doesn't shoot. So they figure, who knows, maybe they were wrong in some place. Maybe the mathematics is not so good. Maybe God tells them something and they go to sleep upset about it, but that's it. So the women, the cheating women were not shot because the rifles, the handguns didn't work. So what happens next?
How many women are there in the city?
Oh, maybe say 2,000. Well,
All the rest will be
200,000.
shot the day after.
Pardon?
All the rest of the women would be shot the day after.
Yes, all the rest of the women will be shot the day after, which will be an unfortunate ending to this story, because all those rest of the men expected there to be 14, and when the 14 didn't happen, they figure there are 15, and 15 happens to be everybody else in that case. So those are the riddles. I think we are sort of, we got to the time that we wanted. And there are sort of standard techniques to figure out the riddles. And one of them is to try to make it as extreme as possible. Like I said, maybe the stone is very small and very heavy. And in some other examples. And each one of them is supposed to teach you something. And I hope it was interesting.
Very interesting. Thank you. Oh, it was, yeah, I'm going to think about them.
So now we'll have a recording of, Rotem will make the recording for us.
Yeah.
And you'll be able